Olá a todos, boa tarde, bem-vindos a mais um seminário do Departamento de Geofísica. Hoje a gente tem um convidado da Argentina, o Sebastián. A apresentação vai ser em inglês, então eu também vou fazer a apresentação dele em inglês. Hello everyone, welcome to this week's Geophysics Department Seminar. I'm pleased to introduce our speaker for this afternoon, Sebastián Correa-Otto. He's a friend of mine. We collected magnetotelluric data together in the provinces of Misiones and Corrientes several years ago. Well, a quick background on Sebastián. He got his undergraduate and doctoral degrees in geophysics at the National University of San Juan, Argentina. He also attended the international training course on seismology, seismic data analysis, hazard assessment, and risk mitigation given by the German Research Center for Geosciences, the GFT. Sebastián is now a professor at the UNSJ at the University of San Juan and a CONICET postdoctoral fellow, which is the Argentinian National Scientific and Technical Research Council. His presentation today is entitled Seismological Study at the Neuquén Basin, the highest hydrocarbon extraction region by non-conventional methods in Argentina. Before we begin, let me remind you that at the end of this presentation, we'll have a brief questions and answers session, so you may write your questions or comments on the YouTube channel, and I will read them to him. So thank you, Sebastián, for accepting our invitation. And whenever you feel like beginning, the word's yours now.
Okay, thank you, Ariel, and thanks for the invite, and to the IAG and the USP for having me. I'm going to share my screen. Okay.
Okay.
So I'm going to be presenting the results of my research. They were made possible by CONICET and the National University of San Juan, as Gabriel said. So let's begin. Let's start by discussing the main topic which led to this research project, the induction of seismicity due to hydraulic fracturing. Okay. So hydraulic fracturing, or fracking, as is commonly known, it's an oil and gas extraction method by the injection of high-pressure fluids into shale and type reservoirs. These reservoirs and the hydrocarbons obtained from them are known as unconventional, since due to their location, reservoir type, and physical properties, they are not economically viable to be obtained with traditional extraction techniques. And due to the diminishing conventional reserves, oil barrel prices, global market changes, and the implementation of new technologies, fracking has been on the rise since 2005. This is a controversial topic due to the environmental problems associated to the activity, particularly the induced seismicity. It's not only controversial, but it's underdocumented, as you can see in this 2017 graphic by Grigoli, all through the years up to 2012, 2014. There were not a lot of articles made on the subject. And according to Dr. Atkinson, up to 2015, it was common to find, even on scientific literature, affirmations that the possibility of generating a damaging earthquake due to fracking was practically zero. When I started this research in 2014, the geological formation Vaca Muerta was already being exploited for non-conventional hydrocarbons, and this formation is located in the Neuquén Basin, which you can see outlined in green here. My study area, where the formation is exploited, is marked by this rectangle. And that formation is very, very important because it was catalogued by a study made by Badesic as third in recoverable gas and oil, fourth in oil at the worldwide scale. So it has a lot of reserves. And you can see also here with the orange dots all the seismicity from the USGS earthquake catalog up to the year 2015, There were no records of seismicity ever registered on the study area. You get the same result if you use the catalog from from the National Prevention Institute, Seismic Prevention Institute in Argentina, or the International Seismology Center, or any other catalog you may look up. So let's take a look at what's happening now. This is a zoom in to the study area, as I previously said, is located between the 37 and 39 degrees south and the longitudes of 17 to 71 degrees west. It contains the exploration and exploitation region of the Vaca Muerta Formation, which is outlined here with different colors from types of fluids that can be extracted. And to better understand the seismic activity at the basin, we installed an 11-station broadband seismometer network in October 2014. Okay. So we wanted to study both the natural and base seismicity and being able to differentiate from the induced seismicity, if any, on the area, both of which were not documented or registered. So our main goals were to properly set the seismological equipment in order to register seismicity under the average magnitude threshold defined for seismically active zones, to develop and improve algorithms and software for detecting and processing such seismicity, integrate different geophysical methods to seismologically characterize the area, establishing its base seismicity and its seismogenic structures, and finally, being able to recognize events triggered by human activity. The last point was to determine if the hydraulic fracturing operations were inducing seismicity. And the thing is, we didn't just want to register small events. We actually needed clean records to apply advanced seismology methods and characterize the area. So this presented a challenge to a research team, since mostly previous projects and research have mainly focused on traditional seismology, on seismologically active regions. And due to the scarce literature and software available to properly process this kind of intraplate seismology, we needed to develop or modified methodologies which would let us carry on all these objectives. So for the geotectonic setting, my research is mainly focused on the mathematics and software adjustment of seismological data. I would rather actually have a geologist doing this part. But as a quick summary of the tectonic setting, you can see the main geological features of the Neuquén Basin in this larger picture of the area that was made by Ramos. And of particular relevance to this seminar, the zoom-in area to the right, I'm going to describe the most relevant structures to my study. In dotted black lines, you can see the north and south border of the Winkle system, or the Winkle Ridge, which is described as an intraplate belt, which is perpendicular to the Pacific convergent margin that accommodated both contraction and transpression deformations during the Jurassic period. Inside, in gray, you can see the main structural alignments of the subsoil and outcrops of these features that were defined by Silvestro and Subire. Then to the west, in white, you can see the Agrio fault and thrust belt that was interpreted by Ramos as a compressive retroarc deformation east of the active volcanic front, and it was associated to faults and reverse faults. Immediately to the east, in green, is the Chihuidos structure, is characterized by a series of anticline faults with west convergence, and it has been interpreted as a basement structure which has had diverse uplift pulses. And finally, Cristallini presented in 2009 an integrated map of the upper Triassic and lower Jurassic structures of the engulfment region of the Neuquén Basin, which you can see here in black and white, this area. They use seismic reflection surveys to detail the main grabens and half grabens, faults, and transfer zones that of this extensive stage of the basin. Also worth noting, there are two dams in the area beneath the town of Añelo, which is here on the center, is Los Barriales Dam and Marimenuco Dam. So for equipment, quickly, we use mainly nanometrics equipment, originally Taurus digital recorders and 120 PA seismometers that were installed on rock outcrops when possible, or in 1 to 2 meter holes in concrete boxes that were isolated from the underground. Most of my research is based on this data that was collected from October 2014 to June 2016. After that, the seismological experiment went into a second phase, from which I was able to work with 3 to 5 stations on and off, and mostly using free data from international catalogs. And so from June 2016 and up to March 2020, which is the period I'm showing this seminar, I use events with 2.5 ml magnitude or higher that I could process properly with this data. And for gravity data, I use a combination of satellite data, pre-existing terrain databases that belong to the institute where I work, the IGSB, and some national organizations. And later on, we went to the field and measured some data using a Sintrex CG5 gravimeter over sections of the study area that had presented seismicity already. Okay. For the methodology, I used and helped develop the Seismo IGSB software that was written in Python based on libraries of SPY, SciPy, Matplotlib. This soft can handle large amounts of continuous data records and calculate quality metrics, run an automated detection algorithm and automatic ML and MW magnitude calculation and other tools good for large data sets. I also used Seisan, which is an integrated platform of diverse free softwares. This software was used for most of the routine seismological processing, which are hypocenter determination, manual ML and MW magnitudes, and focal mechanisms determinations. I invert several velocity models for the area using the software Velest, and I used the software RapidImp for full moment tensor inversion. And for the gravity, I obtained satellite gravimetric data from the page of the German Earth Studies Center, the GOC, for the AGM 2008 model by published 2012. The data was corrected by topographic effect and sediments with the Tesseroids direct modeling method by Ueda 2016, and also used OASIS montage and QGIS software for processing and representation of the data. So let's start with the results. Since the start of the experiment, the possibility existed for it to continue in time for many years. So due to the consequent large volume of data to handle, and since it was a new kind of study for a group, we implemented a quality control system through the calculation and analysis of metrics with the aim of helping to automate the workflow in an efficient way and learn details about the installations of the equipment, of field and extensions maintenance too. We calculate over 20 metrics. Among them, we have some statistic metrics, as you can see here, some signal control metrics. We also plot PSD functions to study the behavior of the signal in every channel, in every station, all through the year. This allows us to compare the signals to the min-max levels of the global average noise model and see that they are properly working. And we also, by studying variations of the frequency content, spectrograms let us see the continuous evolution and sudden changes in the signal for every equipment over time. So comparing manual and automatic earthquake detection, the difference in time spent and even on the number of EQs, I say, I don't remember if I say this, but I say EQs a lot. It means earthquake. It's just shorter, faster to say. So a lot of EQs are found is remarkable in favor of the automatic detection, especially if we consider large periods of time. I'm talking about a lot of stations over a lot of years. Visual inspection is reliable, but it's impractical for expeditious reports in situations where speed is fundamental, for example, for early warning or for traffic light systems. Very small events in terms of energy are easy to miss for the human eye. So for my research, I use a combination of both methods, focusing on improving the accuracy of the automatic algorithm. We were able to reduce the time spent by the analyst in about 70% respect to full manual. So when I started this study, I used the average velocity model for continental crust obtained from the global model AK 135 by Kenneth in 95. The first event I worked on was the one that took place on 19 November 2015, which is marked with a star here and IGSV. From here on, I probably talk a lot about this event, and I will be referring to the event or DEQ of 2015. I'm talking about this event on November 19. It was the first ever event registered in the area, both by international and national networks. And even for the National Prevention Institute, the IMPRES, which I'm going to be mentioning sometimes too. But it was not the first recorded by our network since we were working since 2014. We were able to identify seismicity prior to the occurrence of the event, and of particular interest to this study, we recorded aftershocks, which you can see here, where is the cursor. So these first locations allow me to invert the velocity models and greatly improve the calculations of hypocentral parameters. This is all the seismicity recorded by the network from 2014 to 2016, and the seismicity over 2.5 that I was able to detect using some of our remaining stations and the EQ catalogs, and some free data from 2016 to early 2020. And for the analysis and interpretations of results, as well as the integration with the gravimetric results, I use only events that have less than 30 kilometers in error in X, Y, and Z. Mostly the errors are below 15 kilometers, and inside the perimeter of the 11 stations, which is here, are mostly almost all of them are under 5 kilometers. You can see here that there are only a couple of events in red that have these big errors. All the others are very well defined. I then obtain magnitude calculations, both manually and using automatic algorithms. I then cross-reference both results to adjust and correct my previous results and the algorithm, and spent a large amount of time tuning in the software and the automatic algorithm, tampering with the instrumental response files, since we periodically changed the configurations of the sensors to get better registries. We needed to capture low magnitudes but not get clipped in the case of large events. And here are some of the ML magnitude maps. We got better results using MML, the regression curves for the magnitudes of all the data just fit better. Common misconception with this induced seismicity and fracking is that seismologists used to claim that the actual drilling and fracturing would cause a large IQ. And this is not the case. Seismologists know that a 2 or 2.5 EQ must be caused by the reactivation of a pre-existing fault. I'm going to talk more about that later, but having cleared that out, EQs on the study area over 2.5 have been plotted in orange here. So these orange zones would be indicating pre-existing critical stress faults, which has a sufficient enough area to host such an event of 2.5 ml magnitude or more. And this would be the seismogenic hazard that we have to look for. Then I made a quick histogram on some of the regions, so we can see the two distinctive sections. There's a distribution here, centered around 1 and 2 ml. This is mostly due to the microseismicity. I mean, microseismicity as defined by Ellsworth under 1.5, registered between 2014 and 2016, while the higher magnitudes around 2.3 and 3 are due to the Qs that I was able to compile between 2016 and 2020. So another result we got was we configured the HyDROCARBon software to relocalize the seismicity using a double difference method. This was very useful, mostly before we had reliable velocity models. Making it work was rather difficult, specifically applying the algorithm to large data sets. It runs best and gets better results for events inside the network and covered by at least 4 stations. It greatly improves the depth of the events with large errors on this parameter. My current model is almost as effective with traditional locations as with relocalizations. You can see here in red, this is an old model. In blue are the data relocated, and in green are the same data with traditional location with the newest model, and there's barely any difference between them. So it's good for large data set contained inside the stations, and it's very good to improve the depth parameter. Then I will show you some focal mechanisms of the ones we obtained. This in green is the mechanism obtained for the EQ of 2015. We published a paper in 2018 with all the details. But for the purposes of time, I'll say it had a low degree of uncertainty in its planes, as was calculated by hash, and a dextral strike slip plane that we chose as preferred, with a strike of approximately 65 to 75 degrees north. And the last result in seismology is this was hard to implement too. It's not making it run, but to obtain good results, it was the full momentation tension inversion. With these low energy events and in this region that it's not seismologically characterized, I meant it was hard to get results that actually correspond to the geology features around the hypocenter. I was lucky enough to study with the developers of RapidIM in Germany, and this helped a lot. I was finally able to obtain some MTS using both local data and teleseismic data from arrays of stations. I always liked the software because RapidIM was developed to have a quick response time and was being used when I started working on it with it as a part of the Indonesian tsunami early warning system. So my thought was this could be helpful for traffic light protocol, for decision making, for example, since we have all these local stations and Chile's dense regional network and station arrays that were accessible by the software. So these are some of the exit files for the event of 2015. The DC mechanism, the double couple. It's very consistent when the one that I obtained by both using FogMech and Hash, 2 different software for making focal mechanism. The CLBD, the compensated linear vector dipole, it's a feature usually present on events where there was, of course, other forces present besides the double couple. So the CLBD represents the forces of movements from the source point that are not contemplated by the DC. So these will be forces that occur in different directions, generated, for example, by changes in the pressure made by general external agents, such as the injection of fluids at high pressures. There's also evidence of expansion, as notable by this isotropic component, which is 32%. Excuse me. As for gravity data, before my PhD, I worked with potential field methods, magnetometric, electric, gravimetric methods. It's been always important to me to integrate different methods in geophysics to reduce the inherent ambiguity present. So I decided to include some gravimetric studies, which were very helpful, especially at the start of my research, when I had no seismological knowledge of the area. I used them sometimes as constraints or support, but were mostly useful for adding a degree of confidence to the EQ's location, to see in particular. The regional anomaly was estimated at h40 kilometers to look mainly for tall cortical responses of intermediate to shallow depth, This was, of course, the range of interest to us because it was the range of the depths of the EQs. After much filtering and cleaning up, the combination of data bases had a deviation of approximately 0.3 and an approximate error of plus minus 3 milligal. So to infer the depth and the location of different geological domains, it is necessary to separate its influences of the gravity field. So we applied some anomaly enhancement methods. In the first stages of this study, we mainly used the gravity vertical gradient to detect tectonic alignments, specifically at regional scales, and related to high density contrast. We were looking for evidence of rotation in the deformation of the Winkle system. You can see here with inside the dotted black lines. Since the seismicity on the first stages was mainly located on that area, and we also used the tilt gradient method for the area inside and around the network. The purpose was to enhance shapes, edges of bodies that could generate anomalous effects on the gravity field, assuming a vertical contact model, which was supported by some of the focal mechanisms that we were obtaining. Then the MOJO estimation, the MOJO depth model that yielded the best results for my research was the one calculated by Ueda and Barbosa, 2017. It was based on seismological and satellite gravimetric data, discretizing the anomalous MOJO on tesseroids. The crust mantle discontinuity presents a variation from 14 to 54 kilometers in depth. There is an attenuation in the crust in the center of the study area that could be linked to the plume mantle, also interpreted by Bird, 2014. And this was very useful, especially because the depth levels of the MOJO can be added to the velocity model during the hypocenter parameters calculation. And then the final gravity result is it was using the REM fabric that was first implemented by Pike in 1989. We studied the force and direction of the main orientation for the vertical gravity gradient, the TCC. By studying the eigenvectors, we can detect the alignments and observe the deformation in the area. And all these results take us to the seismotectonic analysis. And here are some quick maps showing my data coverage on the left. Okay. On the left, we have in red the shale wells, and in blue tight drilling wells, as the National Energy Secretary informs. And some of the outlined areas are the areas with drilling licenses, along with the stations located in the town of Añelo and both of the dams. On the right, we have the same 11 stations and the registered seismicity, with low errors, the one that I consider for most of my study. And I drew some of the ray paths from the biggest groups of earthquakes to the station to have an idea of which parts of the terrain were being lit by the passing wave, and also added the gray dots for the terrain gravity data. So you can see this center area is very well covered, and that cleared. This is an analysis of the seismicity. On the left here, we can observe three major groups from A, B, and C. A can be subdivided in 4 subgroups, 1, 2, 3, and 4. They form compact clusters, and most of their locations are over some previously recognized faults. B and C seem to be related to some major structural features, but I'm going to focus on group A. Here you have the depth profiles. We can see that groups 1, 2, and 3 have similar characteristics and are very different to group 4, especially regarding depth. They seem to be outlining a single structure each. And if we plot the eigenvectors of the terrain fabric and the seismicity of groups A and B, the groups are aligned with the vectors, and both are consistent with our first findings of the formation on the Winkle system. That's also published. So I'm not going into detail about that now, but the blue arrows are showing how the deformation could be advancing from west to east. By studying the geological background, integrating seismicity with gravity, we can see some repeating patterns or concordances. Possible structures were marked on this teal chart with black lines, but we only took into consideration if they coincide with some seismicity locations or previously recognized structures. There's also a concordance between EQ depths, gravity vertical gradient, and tilt. EQ clusters of certain characteristics would locate on certain gravity anomalies. For example, on a more regional scale, to the south and west of this chart, on this map, you could find positive shallow anomalies, and they coincide with seismicity register there that has very low depths of the C parameter, and also some negative deeper anomalies coincide with with deeper earthquakes, and the same can be seen on the tilt gradient, and it can also be seen on a more local scale. So moving on to the local scale, we can recognize common patterns on tectonic structures, gravity anomalies, depth and magnitude of seismic events, on focal mechanisms too. This could indicate which area should be avoided or work with caution under prevention or contention measures. So from crystalline studies, I specifically remarked the transfer zones, which are plotted in white in the map. They have northeast strikes, approximately 50 to 75 degrees north. These zones are where the fault systems, which is in black, interchange stress, or where the main faults that define the gravens and the half graben sands. Much of the seismicity and major events that were determined occur over these features. In addition, the alignments defined by the groups of seismicity also coincide with changes in gravity gradient. So studying the activity at the north of the Añelo town, I mean groups A, B, and C, over some positive anomaly values, I defined these three areas. We see in here that the changes in the gravity chart match approximately with the direction of the faults. And events that have intermediate cortical depths of 10-25 kilometers seem to occur in this area. The groups are aligned in the direction of the fault's slip, and also aligned with the nodal planes that we obtained from some focal mechanism. In blue, you can also see some structures interpreted from the tilt chart that also match the alignment and of the change in gravity gradient. And as a kind of transition zone, here we can see this group D, E, and F. In D, we can see an alignment of EQs that corresponds with the slip of a pre-existing fault. Also on E, we see this is over the Winkle system border. We can see a sudden change in gravity gradient between the south, where we have this in blue, this interpreted structure from tilt, and this black structure. This is a fault interpreted by Cristallini. Yes. And in F, we have the same case. We have these sudden gradient changes, which I denote with these dotted black lines. And you can see that the alignment of the seismicity always corresponds with the alignment of the gravity gradient, and the structures, be it interpreted by tilt or defined by seismic records. And to the south of Agnello, finally, the groups G and H presents similar characteristics. There are different conditions that we were previously observing. These are reflected mostly on the shallow depths for the events between 0 and 3 kilometers, and lower gravity anomalies. Also, there are some reverse fault mechanisms that we can see on G. They have planes that nodal planes that match the alignments defined by the gravity gradients, which are marked with dotted lines, on both sides, they occur on both sides of the transfer zone. In H, we can see the focal mechanism and the aftershocks of the EQ of 2015. The dextral plane matches this gradient, this sudden gradient in change in the gravity values, and it also matches the Momentation inversion, of course, the full MT. The dextral plane was chosen because it's aligned precisely with these aftershocks, with other EQs in the area, also the predominant strike of the transfer zones, the region, which is 50 to 75, and the dextral plane is 65 to 75. So also the gravity changes, I think I should say that. Interpreting the transfer zone over this event, extending it to the northeast, it matches the transfer zone that found Cristallini, which is this one here. So this makes sense. Yes, this one. So this makes sense also because the 2015 earthquake happened very close to one of the dams, the biggest one, Los Barriales. So it would have been impossible to measure there with seismic studies. So it's possible for them, if we could measure there, we could find the propagation of that transfer zone. And which of these areas that present seismicity then are related to the oil industry? And the answer is, at least for this study, everyone. The relationship between the production of non-conventional hydrocarbons and the rise in the seismicity is remarkable. Not only for 2014 or 2016, which is what I'm showing you with my data. You could just look at the national and international catalogs to directly see that since the activities started in 2011, the area has gone from 0 EQs to over 90, and that's just the ones that the IMPRES publish, which are the ones that are over 2.5 ml magnitude. So comparing that to the last 50 years of no EQs to over 90 in less than, that we know of, in less than 60 years, in 6 years, sorry, we can assume that that's not responding to the natural recurrence of the area. We're seeing that this results in many places of the world, in many studies. There are a lot of authors that have already explained that it may take years to see the results or the effects. The effects are not necessarily occurring in situ over the drilling wells, but it's a change in the stress of the area, moving from a static state to a dynamic one, the real problem. The injection of wastewater disposal in thousands of cubic meters per day, the continuous and large volume of injection of sand and fluids at high pressure may be producing this change and eventually triggering the reactivation of a pre-existing fault. We need to have at our disposal fracture records, injection volumes, well production, dates of operations, injection wells or for wastewater disposal, and the volumes of this water. And this information is hard to come by an official medium and in a publishable manner. So with what I have now, what we have, the question is, why do these zones present seismicity when there are wells all over the place, but only these zones present seismicity? So Agosto Detzel, in a study in 2017, defines that intraplate seismicity is concentrated on cratonic CO2 borders, and it's related to a specific geophysical parameters that reflect different thermomechanical states of the lithosphere. We observe this on this region too. It's covered in detail in one of my papers. Some of the parameters are that we observe free air anomalies with values over 10 milligal. There is low elastic thickness, crustal shortening. There's elevated heat flow by Sigismondi. Yeah, he made a study in 2012 that proved that, and negative S-wave anomalies. And also Messenger in 2010 found geological evidence of Pleistocene deformation. These authors showed that two topographic bulges, one over the South Chihuidos anticline and over near the town or under the town of Añelo, which is marked in red here. They propose that the South Neuquén Basin is still shortening in response mainly to the state of compressional stress, and that the deformation front is being propagated to the east, and so happens this is the area where most of the seismicity has been registered. So this could be then an area prone to generate the seismic activity, where the state of stress change and somehow lead us to induce seismicity. I'm going to talk a little about the November 19, 2015 earthquake. As I said, this was the first event to attract attention over the problematic of induced seismicity in Argentina, and my first work too. This is the information I have obtained since from the event. It was located southwest of the town of Añelo. It had 3.78 ml magnitude and a depth of 3.2 kilometers with a plus minus 1.8 kilometer error, approximately the same depth of the Vaca Muerta Formation. It presents a strike slip focal mechanism interpreted as dextral. It's interpreted as dextral because it can be correlated with the transfer zone between lower Jurassic fault blocks defined for the zone. It's located on alignment which is consistent with this transfer zone, and with observable terrain features on field or on digital elevation models, and with the alignment of its registered aftershocks. Its full moment tensor presented a high compatible DC mechanism as the one obtained by two other focal mechanisms with two different softwares. And its isotropic and CLBD terms are high and indicate the influence of external factors such as injection or changes in pressure which could be related to expansion. So to define if this is induced seismicity, let's study the criteria defined by Davis and Froelich in 1993 for an earthquake to be considered induced by fluid injection, combined with some of the new discoveries. So they ask, are this event the first earthquake of this type known in the region? We saw that over 50 years of reliable seismological records from several institutions, there was no record of any EQ of any kind before the November of 2015. Then, is there a clear correlation between injection and seismicity? And are the epicenters close to the wells, less than 5 kilometers? So we saw a direct relationship between the increased seismicity over the rising non-conventional activity, and also the epicenters are located near at least one well, at least one. The fourth question, do some of the earthquakes occur on or in the vicinity of the injection depths? We just saw that particularly the 2015 EQ was at exactly the depth of the formation, including the error, and most of the activity on the south of Añelo has that depth, 0 to 3 kilometers. If not, are there known geological structures that could channel the flow to the earthquake sites? We took this on over the seismotectonic study. We noted several structures that had relationship to the geophysical methods applied, and we even have evidence of new structures that were not mapped before. And finally, do changes in fluid pressure on the bottom well are enough to foment seismicity? So this has been answered by many authors now. For example, Atkinson in his 2020 paper explained that the activation of an anomalous event with ML superior than 2 requires a source of a stress perturbation. This is a pre-existing fault that has to be in a critical stress state with a large enough area to host a fault event and a coupled mechanism that could connect both the source to the fault, be it directly or indirectly. So as I mentioned before, this changes the common belief that the actual hydraulic fracturing would cause such an earthquake, which used to discredit the induced seismicity. Now we can firmly state that this is, in these cases, a non-microseismic event with magnitude larger than 2 can only be generated by the reactivation of geological faults. And it's this reactivation what can be triggered by fracking and its associated activities. So for conclusions on a more regional scale, we published the first seismicity report in the Foreland region of the Neuquén Basin between 38 and 39 degrees of latitude, specifically around the town of Añelo, the main stage for the exploration of and extraction of non-conventional hydrocarbons. South of the map, the seismicity and the terrain fabric from the vertical gravity gradients suggested alignments on the Winkle system, similar to the ones described by the structural study of Silvestro in 2008. West to east, these alignments are northeast southwest, east-west, a rotation to east-west in the center, and then a possible new rotation to east, southeast, west, northwest direction. This rotation in directions of the structures matches the interpretation of the Winkle structure as a summatory of deformation events with changing stress through time, being first extensional, then compressive with an orientation that was rotating from north to northwest to east, west, and finally southwest, according to the convergence vector between the Farallon and the Nazca plate and the South American plate. On a more local scale, around the town of Añelo, the registered seismicity and the gravity anomalies are connected to the main faults that define the late Jurassic graben and half-graben system and its transfer zones. The focal mechanisms obtained and the gravimetric enhancement methods also match these results too. And it is proposed that these are some of the seismogenic structures that gravity gradients that were not previously interpreted. The reactivation directions of the structures are consistent with the SH max directions. These are the horizontal maximum stress studied by Warhol breakouts by Guzman in 2007. And in general, with the average ASH max obtained in that same paper, which is close to 90. So these features indicate east-west compressive stress related mainly to the plate border and the Andean topographic forces. But besides this main stress, for this result, different theories were studied as the origin of the seismic sources. First, major control over the localization of the seismicity in the basin could be related to favorable thermomechanical conditions in the Winkle system. Second, earthquakes on the area could be also related to the propagation to the east of the active Andean front and the development of the Añelo anticline, which you can see here in red, as was defined by Messenger in 2010. And finally, of course, the influence of intense fracking operations could be the trigger mechanism or stress alteration reasons that lead to this, to the released elastic energy stored on these pre-existence faults. As a final summary, the 2015 earthquake of 3.78 ml was probably the first ever induced event registered in the area by the reactivation of a pre-existing strike slip fault. Zones favorable to generate seismicity and possible seismogenic structures were studied and interpreted, all of which should be avoided or exploited with caution. Lower Jurassic structures in the area could be the main source of seismic hazard on the area, particularly the transfer zones between these structures. The seismic registry and its continuous increasing numbers were studied in relation to the increasing oil activity in the area through non-conventional extraction techniques. And finally, it's highly probable that in addition to the microseismicity expected to be generated by this kind of anthropogenic activities, tectonic activity could be induced by the reactivation of pre-existing faults. Because of these conclusions, regarding the induced seismicity around the town of Añelo, dense monitoring and response protocols are the first step to approach seismic hazard and risk mitigation on the area. Presently, only retrospective strategies are not enough to protect critical infrastructure. Real-time monitoring with good coverage and fracking operations mapping can be most promising operation method, control method. Bigger development techniques and real-time prevention and mitigation strategies are required that can be verified and applied to future operations. That's all. Thank you for your attention.
Thank you, Sebastián, for your presentation. It was really interesting to see what you have been working with. Let's open now for questions. Anyone that is watching us on YouTube may write there, and I will read the question to him. So let me take a look at YouTube to see if there is any question. Okay, we have two questions here. First one from Lucas Schirber. Why do earthquakes with magnitude greater than 2 have to necessarily happen on pre-existing faults?
Yes, so the concept is that a fracturing well doesn't have enough area to produce a movement that would release that energy. Other known mechanism that could liberate so much energy would be the collapse of a very big space, a very big mine, an atomic bomb. So just by fracturing a horizontal drill, which they use for fracking, is not enough to release so much energy. So that's why we know there has to be a larger area fault that is being reactivated.
Thank you, Sebastián. And another question from Marcelo Bianchi. What is your catalog completude curve to allow you to conclude about the influence of the local human activity to the seismicity? Any comments on the B values?
Yes, actually, the B values, we're working on that. We have left them on the side for now. It's very hard to work with completude catalogs when you're not studying a tectonically active region with a constant state of stress, since maybe in a year they change the patterns of where they drill or where they inject up to 30 to 50,000 meters of water at 1 kilometer depth. So it throws all your curves all the way around. So we actually don't know what to do with that now. Also, we think we need at least 5 years more of records to actually have a good catalog to work on completeness. So mainly my studies are shown all with what you can see, this data, what we didn't see for 50 years and we would see what we see now.
Thank you, Sebastián. Anyone else has any question?
Yes, I may not have understood very well, but the relation of the earthquakes, do they depend more on hydrofrac activity or to injection of wastewater?
That's actually a very good question, because there have been a lot of studies actually related to fracking and to the injection of wastewater disposal. Some studies show that in Canada, in the Western Basin, where most of their fracking operations are, events are related to wastewater injection. And for example, in Oklahoma and parts of the United States, they were more related to fracking. Or we're actually not sure in Neuquén, in Argentina, to which they are more related, of is both, because we need more data from the actual production volumes, which I know where the drills are, the wells, but I don't know which are operational at which time. So that would be a very good point to continue studying.
And do you have a good cooperation from the industry? Do they give you data from the amount of injection, the volumes of injection, or the activity of fracking activity and things like that? Or is it difficult to cooperate with oil industry?
It's very hard, because they have this kind of jealousy. They don't even like to share data with each other. We joke and say that they don't like to share even inside the same company. So it's very hard to get actual data, even from official statements. Of course, I get some data on the down low, but I never use it or try to influence my decisions by that. It's just some stuff that but I try to just stay with what I can get from the national agencies and what I can see from my data, and work on that alone.
Okay, thank you.
Thanks.
Thank you, Sebastián. And there is another question on YouTube from Lucas again. He asks, doesn't fracking involve injecting large amounts of water back into the subsoil? The water being injected could lower the pore pressure significantly.
Yes, it could. That was also why Davidson Froelich asked if there is any structure that may connect these fluids to another structure that could be activated. Some of the lower, the less depth events may be directly involved, as Marcelo asked recently, with the fracking. These fluids, these are fluids which a lot of sand, actually have seen them with my eyes, and over 500 chemicals, they are injected in very big pressures, in very big volumes, and they could lower fluid pressure and activate a pre-existing fault, especially if they're close, in less than 5 kilometers, and the fluids can migrate to this fault, which of course has a vacuum in pressure for the fluid to fill. But it's not the only mechanism that we know of that could unchain damage in earthquakes on an area. But it's the fluids moving to a fault that are the problem, not the fluids on the horizontal directed perforation.
Thank you, Sebastián. And I think that's it. Both Marcel and Lucas, who have asked questions, are congratulating you for the presentation. So Orlando also. So thank you for accepting our invitation. Thank you for your presentation. And
okay, thanks again for having me.
Okay. Gabriel, can I ask another question?
Yes, you can. I didn't hear that. So, okay, one more question.
Okay. Sebastián, the Momentation inversion of the 2015 earthquake has a very large CLVD component. Is this common in other earthquake mechanisms in, say, in the US or Canada? Or could this CLVD component be a result of more complex fault geometry?
Yes, it's actually very high. It was a source of doubt for a long time, but I always get the same results. It's either my data is faulty somehow. I use a lot of arrays, the one in Antarctica, one in United States, for being able to run it properly. But I don't know any other mechanism with such a high rate. It could be that my data, because I'm using so much teleseismic activity, is showing some higher value than the actual value, or that it's the result of a very complex process, which, since it's on that very large transfer zone, I think it could be possible, but I would really need to look it over. But of course, I need to keep working on that.
Okay, thank you.
Okay, thank you. Sorry, Marcelo, I didn't hear you asking for another question. So, okay, now thank you, Sebastián. Thank you, everyone, for watching us.
Okay.
Goodbye.
Goodbye. Thank you for having me.
O Alexandre, quando você quiser